Okay, so we're going to start this review for exam 1 on algebra functions, limits, and derivatives. And we start with simplifying a expression involving exponents. So let's just start here. So it's going to be equal to, and I like to work with this negative first. So a negative in the exponent basically moves the top to the bottom and the bottom to the top. So this is going to be equal to, still something squared. You're going to have this vinculum here, and the bottom here is going to go to the top. So you just copy it down. So x squared y to the negative 1/2. And then on bottom, you copy down the top. So you have a 5 and x to the 3/2. And then y cubed. And that's it. All right, so once I've dealt with that negative, then I'm going to deal with this square. So what does a square do? You square each term. So you square this term, you square this term, you square that term, you square this term, you square that term. So that's going to be equal to x squared squared. So you multiply the exponent. So you get x to the 4th. Y to the, and you're going to multiply exponents. So negative 1/2 times 2 is negative 1. All divided by, and then 5 squared is 25. And then 3/2 times 2 is x cubed. The 2's cancel. And then finally, y cubed, if you square it, you multiply 3 times 2, you get y to the 6. So remember, when you're working with exponents and you want to know what to do, you simply come up with a silly little example. So like 2 squared quantity cubed. So do you add exponents or do you multiply exponents? So 2 squared times 2 squared times 2 squared is actually 2 to the 6. So you actually multiply exponents here. And so then this is going to be equal to, if you have negative in the exponent, you put it at the bottom. And so I'm going to have a y to the 6 times y in the bottom. And then I still have this 25. But here, the x to the 4th and x cubed, these are going to cancel with 3 of these. So I'll be left with 1 of them. So I have an x on top. And so my final answer will be x divided by 25 y to the 7th. All right, so let's move on to number 2. So in number 2, we're going to solve some equations. So we're going to start with this exponential equation right here. So the idea is we need to get to the x, and the x is in the exponent. So how do we reach exponents, or how do we undo exponents? Well, we use the inverse of an exponential, which is a logarithm. So what we're going to do here is we're going to ln both sides. And when we ln both sides, these exponents can come down in front. That's a property of logarithms. So these exponents come right down in front. So I get x ln of 5 is equal to x plus 3 all times ln of e. And then remember, ln of e is 1, so you can drop that off because it's just the number 1. And so we have x ln of 5 equal to x plus 3. And this is really a linear equation. So to solve a linear equation, the idea is get all the x stuff to one side. So we'll subtract x from both sides. And we'll get x times ln of 5 minus x equal to 3. And then this is the tricky part. This is the part where students typically get stuck. What you need to realize is that you can factor out the x here. So x times ln of 5 minus x. Yes, I do not know what ln of 5 minus 1 is, but I can factor out that x, and it's times ln of 5 minus 1, and that's equal to 3. And so then, that's a 5 there. And then so I'm going to divide out. I'm going to divide out by what? I'm going to divide out by this ln of 5 minus 1 on both sides. So ln of 5 minus 1. And I get my answer. So my answer is x equal to, right, so these cancel. X is equal to 3, all divided by ln of 5 minus 1. And be careful, this is not ln of 4. Right, ln of 5 is at some number, and you're taking away 1 from it. Right, and you can check your answer by plugging back in here for x. So as a quick example, right, always important to be able to check your work. What I can do is I can plug in 3 divided by, left parenthesis, ln of 5, in parentheses minus 1 in parentheses. So there's that answer. And to check it, I can do 5 raised to it, and I get out that number. Or I'll pull up that last entry, so that answer again, and I can do e, so second ln, raised to the second answer, plus 1. And if I get back 2,758 point blah blah blah, I did it right, which says I didn't. So what went wrong? Let's take a look here and see if I can see what went wrong. So I put it in wrong, didn't I? Okay, so here, let's do it again. So second enter, see I put a 1 there, I should have put a 3 there, so second enter. Okay, so here's that answer there, and then I want to do second ln, and then I want to do second answer, and I want to add 3 to it. That's what happened, add 3, and that changes everything. And so I get the same answer, therefore I know I did it correct. Okay, let's move on to part B. So on part B, I'm going to solve a trigonometric equation. So to solve a trigonometric equation, I have to know a little trigonometry. So the first thing I want to do is try to figure out where do the angles lie that when you take the cosine of it, you get back 1/2. So I know all students take calculus. So remember, this means that if you have an angle in this quadrant, and you take the sine or cosine of it, it'll be positive. Whereas if you have an angle over in this quadrant, in the second quadrant, if you take the sine of it, it'll be positive, but the cosine and tan will be negative. Similarly for this quadrant and that quadrant, okay? All right, so this is positive, so I know I have to be here, but I'm not here because only the sine is positive, and I'm not here because only the tan is positive, and here. So I'm going to have 2 angles. And what I need to do, and you can draw them, it doesn't matter, you know, but I need to find these reference angles here and here. And so to find the reference angles, I have to know a little bit about how the cosine and sine work. So I need to find basically the sine or cosine, in this case the cosine, of these angles. So 0, pi over 6, pi over 4, pi over 3, and pi over 2. And so here's the cosine of theta. And so I know that the cosine of 0 is 1, so this is actually root 4, then it goes root 3, then it goes root 2, root 1, root 0. And these are all divided by 2. So divide them all by 2. Okay, so then it's really easy to figure out, well, here's 1/2, and so the reference angle is pi over 3. And so this reference angle is pi over 3. This reference angle down here is also pi over 3. And so to find this angle from here to here, it's very simple. It's just pi over 3. So one answer would be x equals pi over 3. And then remember, I can add any multiple of 2 pi and wind up back where I started. So plus 2 pi n. And n is not just any number. N has to be an integer. It could be 1, 2, 3, 4. It could be 0, but it could be negative 1, negative 2, negative 3. So remember, it's negative 2 pi means go the other way, so around clockwise. And then the last answer, there's one more answer here. X is going to be equal to, I need to find this angle from here to here. There's several ways to do this, but the best way, the one that actually works always, is you think you go, and that's from here to here, sorry, all the way around from here to here. The best way is to think about going all the way around 2 pi. That goes all the way around to back where you started right here, but then go back pi over 3, so minus pi over 3. And so that's equal to, multiply top and bottom here, it's really 2 pi over 1 by 3, and you get 6 pi over 3, minus 1 pi over 3, which is 5 pi over 3. So my second answer would be 5 pi over 3, and again I can add any multiple of 2 pi, so 2 pi n, where n is an integer. So when I say any multiple, I mean any multiple of 2 pi, where n is an integer. And so that's my answer for this one. Again, you can check your work simply by using your calculator. And so if you take the cosine of second pi divided by 3, hopefully I get back 1/2. If I don't, I did something wrong. I do, so I'm okay. And then I could also do the cosine of 5 pi over 3. And again, hopefully I get back 1/2. Otherwise, I did something wrong, and I do. And so I'm pretty sure that I have the right answers. All right, let's look at the last one, or number 3, basically. And so number 3, I need to find the domain and range. And so I'm going to use colors here to help me. And so remember, domain is input. So it's like I'm looking for things above and below. So I'm good, I'm good, I'm good, I'm good. The only issue you might have is when you get right here, you have an open circle, but below it's closed. So you're good, you're good, you're good. Again, issue, open circle, but it's closed above. So if you plug in 2, you get out 2. So it has an output, so it's good, it's good, it's good. And so it's everything. So minus infinity to infinity. For the range, we'll use red. Now for the range, you go on the output on the y-axis, and notice this arrow is going down, so it means it continues to go down. So you're good, 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 good. The only question might be if you get right here, there's an open circle, but put to the right, there's a graph, and there's even a graph to the left, so you're good, you're good, you're good, you're good. Again, an open circle, but it's closed right here, so that's good. Good, good, good. And now this is a horizontal asymptote right here, so this end of the function is approaching, but you have a closed circle, so that means you include 2. So it's all the way from the bottom, so from minus infinity to 2. And you include the 2. All right, let's wipe off the color because we're going to start again with doing increasing and decreasing. So for increasing, we'll use red. And so for decreasing, we'll use red, and increasing, we'll use green. So yes, you're decreasing, you're decreasing. If I could trace this correctly, you're decreasing, you're decreasing, you're decreasing. And then you're going to increase from about here to here. And then, of course, you're going to decrease again. So you're decreasing from here to here. And then you're going to increase again from here to here. Up, 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 up. And then you turn around and you go back down and you decrease from here to here. So when you color it, it's really nice because it's simple to write. So it's decreasing on the red stuff. So you start at minus infinity, and you're decreasing, 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 decreasing. You're always giving me the inputs to -3. Union, and then you pick up here at -1 and go to 0. Right, there's 0 here. So -1 to 0. And then you're decreasing again from 2 all the way out to infinity. So union 2 to infinity. And they're increasing every place else. So you're increasing from -3 to -1. So you're increasing -3 to -1. Union, and then this one goes from 0 to 2. So 0 to 2. All right. It's really easy to find maximums and minimums. It's where you change color. So you have a local minimum right here. So f of -3, which is equal to -1. You have a local maximum right here. You went from green to red, so locally it's a high point too. So f of -1 equal to 1. And you could even argue that this is a local minimum because you're going from, it's a low point. We could say it's going from red to green, really. So it's a local minimum, so I would put 1 there too. So f of 0 equal to -1. And then this one goes from green to red, so you could argue this one too is a local maximum. So certainly locally it is a high point. So over here you could put f of 2 equal to 2. Now you can't say f of 2 equal to 1 because notice 1 is not an output value, it's an open circle. So be careful with what you think is a local maximum or local minimum. But if you stick to this rule, it's sort of where you change color from increasing and decreasing. You can't go wrong with that. All right, let's go down to concave up and concave down. So let's erase this again. We'll start over with our colors. And what's nice about concave up and concave down, it's really a play on increasing and decreasing in some sense. And so we'll use, for concave down, we'll use red. So it's definitely part of a frown. So it's concave down. And then we switch over here to a smile. So I'm going to stop right there. You should stop at kind of nice points. I switch over to a smile, and it smiles right here. But then it certainly goes into a frown again. So I'm going to stop there at that nice point and then turn into a frown. And then I switch over into a smile again. That's definitely part of a smile. All right, if you ever question whether to smile, just put 2 points and, oh, it's smiling at me. And then it definitely turns to a frown. So this is concave down, and it's also concave down over here. All right, so for concave down, it's all the red stuff. So you're concave down from here to here. So I would say from from negative infinity to -4. Union, and then I pick it up at -2 to -1. So -2 to -1. Union, and then I pick it up here at 0 again, and I would go all the way to 2, and I think I would probably stop at 2 because there's a hole there, so I really would say it's defined to be concave down at that point because it's really a point of discontinuity, so it's not even continuous there. So I probably would stop it there, so from 0 to 2, and then union from 2 to infinity. So union 2 to infinity. And then it's concave up where it's green. So from -4 to -2. So -4 to -2. Union, and then -1 up to 0. So -1 up to 0. And again, if you color code it, just like we found local maximums and minimums, it's where we change color. For inflection points, again, it's where we change color on concavity, so where we change concavity, basically. So wherever I see changes in color, I have inflection points. Now, you don't have an inflection point here because you don't change color. You go from red to red, so that's not an inflection point. So I definitely have an inflection point here. That's the point 4, 0. And then I definitely have an inflection point here, so that's the point -2, 0. And then I definitely have an inflection point here because you go from concave down to concave up, so that's the point -1 to 1. And one could argue that you do have a change in concavity here because you are going from green to red. Even though it's a point of discontinuity, it's not really clear. We never talked about continuity with respect to inflection points. So if our definition of concavity, I'm sorry, we never talked about continuity when we talked about concavity and inflection points. So if our definition of concavity is from concave up to concave down, this definitely satisfies that. So I would even put in from 0 to -1 because there is a change in concavity. You go from concave up to concave down. And again, I exclude this one because you don't change concavity. It's concave down to concave down. So I would not refer to it as an inflection point. All right, so the rest of this problem I'm going to pick up in the next video, but I'm going to skip ahead to number 4 because I want to find the domain of this function. So how do we do this? All right, so remember, when you're finding the domain, you have to watch out for basically 3 things, right? The first thing is you can't divide by 0. And the second thing is, if you have an even root, so like a square root, you need to make sure whatever is underneath that radical sign, it's bigger than or equal to 0. And so it's good for any even root. Odd roots you don't need to worry about. And the reason for this is you don't want to introduce complex numbers into our system. We only want to work with real numbers. And then the last thing, if you have an ln function, make sure whatever expression's inside there is always bigger than 0, otherwise it won't be defined. You can't take the ln of a negative number or of 0. So when you look at this function, and you look at these 3 things, you look at the first thing and say, hey, are you dividing by something? And you say, yes, I'm dividing by x. So I need to make sure x is not equal to 0. So the first thing you can write down is x cannot be equal to 0. So on your number line, when we're talking about the domain, the possible things you can put in, you can immediately take out 0. So put a hole at 0. All right, so number 1 is done. We finished off with the denominator being 0. Then we look at number 2. So do you have a square root? And certainly we have a square root. It's right here. So you need to make sure the thing on the inside is bigger than 0. So the thing on the inside, which is x plus 1, not the square root of x plus 1, but just x plus 1 needs to be bigger than or equal to 0. So you subtract 1 from both sides, and you get x bigger than or equal to -1. So here's -1, and it needs to be bigger than or equal to, so it's to the right, and it includes, so we get here, we'll skip over this because we know it can't be 0, but it's everything else to the right. And so our domain D is equal to, we go from -1 to 0, you don't include 0, again, because you can't divide by 0 there, and then union 0 to infinity. And that's our domain. And the last problem we're going to do on this video, I think, so the last problem we're going to do on this video involves composition and deciding whether a function's even, odd, or neither. So here we have two functions. F of x is equal to x squared minus 1, and g of x is equal to square root of x plus 2. Let's find f composed with g of x, and so that's f of g of x. Very important to write down this step because it basically tells you then what to do. So I'll do f of. Wherever I see a g, I'll plug in what it's equal to, so it's equal to this. So I'll put that on the inside, so square root of x plus 2. And then what I'm going to do is I'm going to read off f. So what does f say? It says whatever's here, whatever it is, you're going to square it and take away 1. So now this is my it, so I'm going to square it, so square root of x plus 2, quantity squared, and I'm going to take off 1. And so the square root will go away, so we get x plus 2, and then minus 1, which is equal to x plus 1. And now I want to decide whether it's even, odd, or neither. So there are lots of ways to do this. You could simply make a graph of this, which you really don't need a graphing calculator. So let's just make a graph by hand. And so you have a y-axis and an x-axis. And this is just the graph of the line that passes through the y-intercept of 1. So it passes through 1. It has positive slope, so it's going to look something like that. Right, so x plus 1 looks like this, and so it's neither. It's neither even or odd. Remember, even reminds us like this, and odd is like this. Right? It doesn't go back on itself, but it's like this. And you know, your x and y axis have to be in a nice spot. So here's your y and here's your x. So it splits it right down the middle. And here it splits it right down the middle, but it's opposite. So this is odd, and this is even. So neither of these ideas are captured by this function. So now let's look over here of g composed with f of x. So that's g of f of x, which is equal to g of, and we come over here, and this is my f. So wherever I see f, I'll replace it with x squared minus 1. And so remember g, what is g? Whatever it is, you take the square root of it plus 2. So we'll take the square root, and now my it is this, so x squared minus 1, and we'll add 2 to it. And so that's equal to the square root of x squared plus 1. And that's my answer for that. And remember, the square root does not go through addition, so you're all done. You can't do anything more. And if you look at a graph of this, well, the square root function looks something like this. So I'd imagine it looks a little bit similar, but it starts up here, I guess. So it probably does something like this. So again, it's neither even nor odd. And you can check the graph of this. You know, I've never graphed that before, but you can check the graph of that with the with your graphing calculator. It should look pretty close to that graph.